In this video, we'll learn how to perform multiplication in assembly using only repetitive addition. We will then apply simple mathematical optimizations and techniques to make the multiplication significantly faster. The assembly code will be written in Hack Assembly for the Hack Machine from the Nand2Tetris course, and this program is the first goal of Project 4 of the course. However, the concepts should be easily portable to other assembly languages as well. So let's get started. Given a multiplicand and multiplier, the easiest way to multiply is to simply add the multiplicand to a sum that starts at 0, repeating this process for a number of times specified by the multiplier. This works because multiplication is essentially taking something multiple times. In assembly, we first initialize the sum to 0, then we use the multiplier itself as a down counter and set up an infinite loop. Inside the loop, if the multiplier reaches 0, we exit the loop and enter another infinite loop to signal the end of the program. Otherwise, we add the multiplicand to a sum, decrement the multiplier, and return to the start of the loop to repeat the process. The code is very simple, but the biggest problem is that it is extremely inefficient. Assuming the operands are greater than or equal to 0 and the product is always less than 32,768, the worst case occurs when we multiply 0 or 1 with 32,767. The 12 instructions inside the loop result in a total of almost 400,000 instructions. The solution is also easy to see. Check if the multiplier is greater than the multiplicand, and if so, swap them so that the smaller operand is selected as the multiplier. In Hack Assembly, we can only compare a value with 0, so we compare the difference with 0. To perform the swap, we can either store a value temporarily in RAM or, given our assumptions, swap the registers in place using only addition and subtraction. We first compute the difference between the operands and use a jump instruction to skip the swap if the difference is greater than or equal to 0. Otherwise, we perform the swap by storing the sum and then subtracting each register value from the sum to get the value of the other register. Now, the worst case occurs when the operands are equal and the product is closest to the maximum of 32,767, which happens when we compute the square of 181. The loop still contains 12 instructions, so in this worst case, approximately 2000 instructions run in the loop. This is already 200 times better than before. But if I ask you to perform this multiplication by hand, you would never do 181 additions. Instead, you'd use a much faster method for multiplication, so why don't we do that in our program as well? First, let's derive the algorithm for the steps we take. At each step, starting from the least significant bit of the multiplier, we multiply the bit with the multiplicand, shift it to the left depending on which step we are in, then add all the products together. We can use a running sum like before to store the sum at each step. Then we make further observations to optimize the algorithm. The first observation is that we can switch the order of bit multiplication and shifting. That is, we can shift the multiplicand first to the left and then perform the multiplication. This optimization enables the next optimization. Instead of performing multiple shifts at each step, we can shift the multiplicand by 1 in place at each step. Now we need to extract individual bits from the multiplier at each step. We can exploit the properties of the AND operation for this. Since AND of a bit with 0 is always 0 and with 1 is always the bit itself, to extract a bit of a value at some position, we place 1 in that position and 0 in all other positions. Then perform AND with the value. If the result is all zeros, this means the bit itself was 0, otherwise the result will be a non-zero value since it has 1 at that position. To create the bit marks with 1 at the specific position, we can shift left 1 by the position amount, but like optimization 2, we can also shift left the value in place by 1 at each step to place it in the correct position. Now we can use the result of the AND operation and compare it with 0. If the result is 0, the bit was 0, so the product with the multiplicand will be 0 and the sum does not change. If the result is non-zero, the bit was 1, so the product with the multiplicand will be the multiplicand itself, and therefore we add the shifted multiplicand to the running sum. Finally, we need to implement the shift left by 1 operation. Since the Hack Machine and Hack Assembly don't support it directly, we'll use simple mathematics again. To shift left is to append a 0 at the end, which also happens when we multiply by 1 0, but 1 0 in binary is 2, which means by multiplying by 2 we can perform a binary left shift on a number. To multiply by 2 is the same as adding a number to itself, so to shift left we can simply add the value to itself. Now we are ready to write our final code. We could use the previous swap algorithm to keep the multiplier smaller than the multiplicand, but this is not needed here because we'll always run the loop a fixed 8 times using an additional variable called down counter. 8 loops are sufficient for our worst case scenario when we square 181. We need another variable to store the left shifted 1. Now we initialize a running sum as 0, then create a loop. Inside the loop, we AND the multiplier with shifted 1. If the result is 0, we don't add anything to the running sum. Otherwise, we add the multiplicand to the sum. Then we shift the multiplicand to the left by adding it to itself in place. We do the same for shifted 1 as well. We decrement the down counter. If the down counter becomes 0, we exit the loop and enter the infinite end loop. Otherwise, we return to the start of the loop. Now the loop contains 22 instructions and runs 8 times for a total of only 176 instructions. This is about 10 times faster than the swapped addition and 2000 times faster than the no swap addition method.